have a reaction, and it says you have 0.5 moles each hydrogen, H2, and sulfur present initially in a 1.0 liter flask. The system is allowed to reach equilibrium at 90 degrees Celsius. There is 0.032 moles of H2S present at equilibrium. What is the equilibrium constant, Kc? So from the lecture outline videos, you probably remember that there are two kinds of what are called ice table problems. This is the first kind. So first off, this is an ice table problem. And it's the kind of problem where we're finding the equilibrium constant, which is Kc in this case. And ice tables are something that you'll get to practice on the recitation today and of course on the homework. But ice tables look like this. So make a little table across, and so this will be the first row, and on the top of the first row, write the reaction. And the way I do it is I put the units for the ice table up here, and ice tables only really have two sets of units. If it's a Kc, it's going to be molarity, and if it's a Kp, it's going to be atmospheres. So since it's Kc, this is going to be molarity, so I put my capital M there, and then I do ICE. I stands for initial concentrations, C for change in concentration, and E for equilibrium concentration. Now, these are molarities, and we haven't been given molarities in our problem statement. We've been given moles and volumes. But since the volume is 1 liter, 0.5 moles divided by 1 liter is just 0.5 molarity. So I'm going to put 0.5 there, or 0.50. My sulfur is a solid. We said solids don't show up in equilibrium constant expressions because solids don't have concentrations. And so whenever I see a solid, what I tend to do is put a big X below it. And this is just basically to cross out this column. We don't need this column in our ice table because solids don't appear in equilibrium constant expressions. Now, there's no mention of any product. Typically, most reactions, there's no mention of the product having an initial concentration, so we'll put a 0 there. And there is a mention of H2S having moles of product present at equilibrium. So that means whatever this is in terms of molarity must go down here in the equilibrium row. And I think I did this on the lecture outline too. There are 3 rows here, and what we're saying is that the concentration of our H2S is 0.032 moles per liter. That's why this number goes here. Jump in anytime if you have any questions. Now, this is enough information to figure out all the numbers in the ice table. For example, if you start with 0 molarity H2S and you end, or at equilibrium, you have 0.032 molarity, then, actually I'll do this in another color because this is what we're figuring out. Then the change in concentration of H2S must have been plus 0.032. And if 0.032 molarity H2S was produced, then minus 0.032 molarity H2 must have been reacted away. And what we'll see is that the changes in molarities, or the changes in concentration in this ice table, always rely on or always use the coefficients. Changes in concentration always use the coefficients. And the coefficients in this problem happen to be 1s, so, but we'll hopefully see some problems where they are other than 1. In fact, I know we will. Okay, so now all that's left to do is we go ahead and do the subtraction here. 0.50 minus 0.032, 0.468. I write that, but then I want to do it in calculator anyway. Yes, good. And finally, we are trying to determine the equilibrium constant, Kc. Kc expression is products, here, products raised to coefficients, which is just 1, over reactants raised to coefficients, don't include solids and liquids. So our equilibrium constant expression is written right here. Then we take our equilibrium concentrations and plug them in. And solve for Kc. I get 0.0684. And good news, this is one of the choices, 6.8 times 10 to the minus 2. Any questions about this?